Greetings, everyone! Today, we set out on a captivating exploration of how the mole serves as a crucial link between the expansive macroscopic realm and the intricate microscopic world. As representatives of the Serum Group, we are eager to unveil our findings and perspectives. Our journey will be structured around the following key topics: understanding the mole, exploring the atomic mass, investigating atomic weight, unraveling the complexity of isotopes, and applying the stoichiometric principles. Let's delve into our journey. The first topic that we will discuss is exploring the concept of the mole in chemistry. The mole is a unit of measurement used in chemistry to express amount of substances. It plays a crucial role in quantifying chemical reactions and understanding the behavior of matter at the molecular level. Just as a dozen of eggs or a gross of pencils provides a convenient way to count everyday objects, the mole provides chemists with a means to count atoms, ions, or molecules on a scale that is practical for laboratory work and theoretical calculations. Let's delve into the historical origins of the mole concept and its connection to a prominent figure in chemistry, Lorenzo Romano Amadeo Carlo Avogadro, Count of Corregna and Cerreto. Avogadro, born in 1776 in Italy, was an accomplished scientist and mathematician. He made significant contributions to the understanding of gases and molecular theory. In 1811, Avogadro proposed what is now known as Avogadro's law, stating that equal volumes of gases under the same condition of temperature and pressure contain the same number of molecules. Although Avogadro himself did not determine the precise value of this constant, his hypothesis laid the groundwork for the concept of Avogadro's number. Avogadro's number is a fundamental constant in chemistry. It is an SI unit denoted as N sub A, representing the number of atoms, molecules, ions, or other elementary entities in 1 mole of a substance. Its value is approximately 6.022 times 10 raised to 23 entities per mole. But why is the mole such a crucial concept in chemistry? It is due to its role in quantifying matter at the atomic and molecular level, bridging macroscopic and microscopic worlds, enabling stoichiometry, facilitating molar mass determination, and providing a universal language for chemists worldwide. By standardizing the measurement of substances, the mole concept allows chemists to make precise calculations, predict chemical reactions, and communicate effectively across scientific disciplines. To understand more, let me give you an example. Determine the number of moles present in 12.5 grams of ethanol. To calculate the number of moles in a sample, we will use the formula the number of moles is equal to mass of substance in grams per molar mass of substance in gram per mole. We first need to find molar mass of ethanol. The molar mass of ethanol is calculated by adding the atomic masses of its constituent elements. 2 times 12.01 grams of carbon plus 6 times 1.008 grams of hydrogen plus 16 grams of oxygen is equal to 46.07 grams per mole of ethanol. Now that we have the molar mass, we can apply the formula to calculate the number of moles. 12.5 grams of ethanol times 1 mole of ethanol over 46.07 grams of ethanol is equal to 0.271 moles of ethanol.
Good day, everyone. I am Gabriela Manicalbornos, and I will be talking about atomic mass. Atomic mass in the field of chemistry serves as a key metric for understanding the composition of matter, defined as the average mass of atoms within an element, expressed in atomic mass units, also known as AMU, or daltons, also known as D. It unveils essential insights into the behavior and characteristics of elements. Atomic mass versus atomic weight. Atomic mass is the sum of protons and neutrons of a single atom, while atomic weight is a weighted average of the mass of all natural isotopes of an element. In summary, while atomic mass focuses on the mass of an individual atom, atomic weight provides an average mass that considers the contribution of all isotopes and their respective abundances within a naturally occurring sample of the element. The key distinction lies in the scope of measurement. Atomic mass is specific to a single atom, while atomic weight reflects the average mass of a group of atoms of a particular element. Now, let's try to answer this question. An element has the following natural abundances and isotopic masses: 90.92% abundance with 19.99 AMU, 0.26 abundance with 20.99 AMU, and 8.82% abundance with 21.99 AMU. Calculate the average atomic mass of this element. So the average atomic mass of an element is a weighted average that considers the natural abundances and isotopic masses of its different isotopes. In this scenario, an element has three isotopes with respective abundances and isotopic masses. The task is to calculate the average atomic mass of the element. To find the average atomic mass, one must multiply the abundance of each isotope by its isotopic mass. Sum these products for all isotopes and then divide by 100 to obtain the weighted average. The formula is as follows: 90.92 multiplied by 19.99 plus 0.26 multiplied by 20.99 plus 8.82 multiplied by 21.99 over 100. When we plug it in the calculator, we get the answer 20.1116 AMU, or 20.11. Therefore, the average atomic mass of this element is approximately 20.11 AMU. Let's try to answer another problem. Atomic mass of boron is 10.81 AMU. It has two isotopes with 80% and 20% abundance. The atomic mass of one isotope is 11, and the mass of the other isotope is unknown. The atomic mass of an element is a crucial parameter that reflects the average mass of its isotopes, taking into account the respective abundances. In the case of boron, which has an atomic mass of 10.81 AMU, it is composed of two isotopes with abundances of 80% and 20%. If the atomic mass of one isotope is known to be 11 AMU, the task at hand is to determine the mass of the other isotope. So to find the mass of the second isotope, we can utilize the weighted average formula for atomic mass. Let us look at our solution. So 10.81 is equals to 80 multiplied by 11 plus 20 multiplied by the mass over 100. So solving for the mass of the second isotope would be 1081 equals 880 plus 20 multiplied by the mass. And then we plug it in the calculator and we get 10.05 AMU. Therefore, the mass of the second isotope of boron is approximately 10.05 AMU. This calculation illustrates the importance of considering both isotopic masses and their respective abundances and determine the overall atomic mass of an element. That would be all. Thank you.
Good day everyone, I am John Pico Palmero, and in this section we're going to discuss the atomic weight, its definition, its differences from the atomic mass, and the calculation involving atomic weights. So what is the atomic weight? Atomic weight is the ratio of the average mass of an element's atoms to some standard. From the term itself, the atomic weight of an element is the amount of mass measured within the gravitational field. Since atomic weight and atomic mass were used interchangeably, this leads to the confusion among chemists and students, and in order to avoid confusion, atomic weight can now also be referred to as the relative atomic mass. The relative atomic mass of an element is the weighted average of the masses of its isotopes and their corresponding relative abundances. Atomic weight can also be measured and expressed in atomic mass units, or AMU. Just as mentioned before, there has been confusion due to the interchanging use of the terms atomic mass and atomic weight, when in fact they have different meanings and calculations. So here are the differences between the atomic weight and atomic mass. First, the atomic weight is the calculated average weight of the element and its respective isotopes and their relative abundances. Remember that the atomic weight is the overall weight of an element including its isotopes. The atomic mass, on the other hand, is calculated by adding the amount of protons and neutrons of a single element or isotope. Note that the atomic mass is the mass of a single element or a single isotope, which means that each isotope of an element has a different value of atomic mass. The atomic masses of the isotopes of an element is different and are not the same from each other. The value of the calculated atomic weight is dependent on the amount of atomic mass of the isotope and its abundance. The atomic mass of an element, on the other hand, is independent of the masses and abundances of its isotopes, since it only depends on the amount of protons and neutrons in an atom. Both atomic weight and atomic mass can be calculated, but in different ways. The atomic weight is equal to the sum of the products of the mass and abundance of each isotope of an element that exists in nature, while the atomic mass is calculated by the sum of the protons and neutrons in a single atom or isotope of an element. Now that we have discussed the differences and how to calculate the atomic weight, let's now proceed to the sample problems involving atomic weights. So for the first problem, the atomic masses of the two stable isotopes of copper, copper 63, with a 69.17% abundance, and copper 65, 30.83 atomic 30.83% abundance, are 62.9296 atomic mass units and 64.9278 atomic mass units, respectively. Calculate the average atomic weight of copper. So, from the problem, we are asked to calculate the average atomic weight of copper. The average atomic weight of copper is equal to the sum of the products of the abundance of the atomic masses of copper 63 isotope and copper 65 isotope. So we just have to substitute the corresponding values. So 69.17% over 100 times 62.9296 plus 30.83 over 100 times 64.9278 atomic mass units. Multiplying all this and taking the sum of these products, we would have the 63.55 atomic mass units. So therefore, the average atomic weight of copper is 63.55 atomic mass units. Now that we have solved this problem, let's move on to another. For the second problem, an element has the following natural abundances and isotopic masses. 90.92% abundance with 19.99 atomic mass units, 0.26% abundance with 20.99 atomic mass units, and 8.82% abundance with 29.99 atomic mass units. So calculate the average atomic mass of these elements. So the element given has three isotopes. So same calculations will be used. We just have to include the third isotope or the third given. So we just have to substitute the given values of the corresponding isotopes and finish the calculations. So 90.92 over 100 times 19.99 plus 0.26 over 100 times 20.99 plus 8.82 over 100 times 21.99, and in order to calculating this, we will have a 20.16 atomic mass units. So the average atomic mass of the given element is 20.16 atomic mass units. And these are the references used for the preparation of this presentation. So thank you for listening and have a great day.
Hi, I am Trillian K. Uy and I'll be discussing about isotopes. As we all know, an atom is composed of three subparticles called the electrons with the negative charge, the protons having the positive charge, and the neutrons with the neutral charge. Atoms of a particular element share the same chemical properties due to its number of electrons. The valence electrons of an element mainly determines its chemical properties. Hence, those elements in the same group have similar chemical properties since they have the same valence shell configuration. However, an element can have a varying physical property due to its varying mass number, which is influenced by the number of neutrons. The mass number of an element is equal to the number of protons plus the number of neutrons. On the other hand, the atomic number of an element never changes, and this means that the number of protons in the nucleus of every atom in an element is always the same. With this, it can be said that the number of neutrons influences the change in mass of a particular element. Hence, these atoms of the same element with varying mass numbers are called the isotopes. One of the primary examples of isotopes is hydrogen. Hydrogen, as the most abundant element in the universe, is the ultimate source of all other elements by the process of nuclear fusion. The most common isotope is protium, which has one electron, one proton, and no neutron, followed by deuterium, which has the same number of proton and electron as the protium, but this one has an additional neutron. The rarest isotope of hydrogen is tritium, which is produced in the upper atmosphere by a nuclear reaction when cosmic rays strike nitrogen and other atoms. This isotope is considered as radioactive, having two neutrons in its nucleus. Like any other atoms, the physical properties, such as mass, melting or boiling point, density, and freezing point of isotopes are different and is dependent on the mass of each isotope. For instance, the different masses of the three isotopes of hydrogen cause them to have different physical properties. Thus, these isotopes differ in their melting points, boiling points, densities, and heats of fusion and vaporization. In an experiment conducted in the year 1931 by Harold Urey, deuterium was discovered by slowly evaporating several liters of liquid hydrogen until a volume of about 1 milliliter remained. When that 1 milliliter of liquid was vaporized and its emission spectrum was investigated, a novel absorption lines were observed which were different from the previously identified absorption lines from a hydrogen. After that, another attempt of the same experiment was made in order to detect the natural abundance of tritium. However, it is low, hence, the third isotope of hydrogen was made through nuclear reaction in the year 1934. On the other hand, all the isotopes of an element have identical chemical properties because they have the same number of electrons as an atom of that element, despite having different numbers of neutrons. One example of this is the isotopes of carbon, which contains 6 electrons. Moreover, isotopes are either stable or radioactive. Stable isotopes are atoms having stable nuclei, hence considered as non-radioactive, or they do not emit radiation. There are two main factors that highly determine the stability of nuclei. First is the ratio of protons to neutrons, and second is the sum of protons and neutrons. A particular element can have more than one stable isotope. For example, carbon isotopes come in three forms, and two of them are considered as stable isotopes. First, carbon-12 is by far the most common isotope of carbon, in which it contains 6 neutrons in addition to its 6 protons. The vast majority of all carbon found on Earth is carbon-12, wherein almost 99% of all carbon on Earth is of this form. The next heaviest carbon isotope and considered as stable is the carbon-13, which has 7 neutrons. Approximately 1% of all carbon on Earth is of the carbon-13 isotopic form. Both carbon-12 and carbon-13 are considered as stable isotopes since they do not decay into other forms or elements over time. Meanwhile, unstable isotopes are atoms that have unstable nuclei, and these are radioactive isotopes, hence its name. An unstable element or radioactive isotopes can be unstable due to the presence of a high number of neutrons compared to the number of protons, or the other way around. The rare carbon-14 isotope contains 8 neutrons in its nucleus, and unlike carbon-12 and carbon-13, this isotope is unstable or radioactive, and over time, carbon-14 will decay into a stable product. A study shows that only 1 out of every trillion carbon atoms is carbon-14. Isotopes also play significant roles across diverse applications considering its exceptional properties. From the equipment used to direct utilization, isotopes have shown their potential in the realm of medicine. For example, cobalt-60 has been used to treat cancers. An external irradiation, sometimes called as teletherapy, can be carried out using a gamma beam from a radioactive cobalt-60 source, though in developed countries, the much more versatile linear accelerators are now being used as high-energy X-ray sources. An external radiation procedure is known as gamma knife radiosurgery, and it involves focusing gamma radiation from 201 sources of cobalt-60 on a precise area of the brain with a cancerous tumor. Worldwide, over 30,000 patients are treated annually, generally as outpatients, and it shows that teletherapy is effective in the ablation of tumors rather than the removal, and it is now finally tuned. Other radioactive isotopes are employed as tracers in metabolic research and for diagnostic purposes. As an example, in a breath test, carbon-14 is utilized to detect the ulcer-causing bacteria, which is Helicobacter pylori. Another example would be sodium-24, wherein it is used as an electrolyte tracer to follow the path sodium takes in a person's body to see if their uptake levels are within normal ranges. In terms of industrial application, cesium-137 isotope has established its importance in the radiotracer technique for the identification of sources of soil erosion and deposition. Lastly, americium-241 has been used in widespread applications, especially in backscatter gauges, smoke detectors, fill height detectors, and in measuring ash content of coal. And that would be all. I hope you learned something from me today. With that, you can check your understanding through answering these questions. Thank you.
Hello everyone, I'm Erica May Habinas, and for the last part of our CRTV for Inorganic Chemistry, I'll be discussing about stoichiometry. And stoichiometry, by definition, is the branch of chemistry that uses the relationships between reactants and or products to acquire desired quantitative data. So this is possible because of the stoichiometric ratio, or the mole ratio, which is a conversion factor that relates the amounts in moles of any two substances in a chemical reaction. And the numbers in a conversion factor comes from the coefficients of the balanced chemical equation. The key here is to ensure balance in our chemical equation, because this is governed by the law of definite proportions and law of conservation of mass and energy. The technique in learning and mastering stoichiometry lies in practice. Thus, we will solve several stoichiometric problems in this video to ponder more on this topic. So, to begin, here is our sample problem number 1. So how many grams of ammonia are produced when 1.20 moles of nitrogen reacts with hydrogen? The problem already provided us a balanced chemical equation. showing that 1 mole of nitrogen gas plus 3 moles of hydrogen gas will yield to 2 moles of ammonia. Aside from that, we were also given the starting materials of nitrogen, which is 1.20 moles. Since no amount of hydrogen was given, we can assume that it is an excess in our reaction. So only the amount of nitrogen must be considered to determine the amount of ammonia in grams, which is our unknown in the problem. The technique in solving stoichiometric problems, especially the long ones, is to always use flowchart, because in that way, we'll be able to trace our process easily. So, we were given the moles of nitrogen, and we have to convert it to the moles of ammonia using their molar ratio because we're concerned on the amount of ammonia. Lastly, it requires us to report the quantity of ammonia in grams. So we have to multiply the moles of ammonia to its molar mass to get its mass in grams. To solve, here's 1.20 moles of nitrogen, which is given in our problem. Then we have to multiply it to the mole ratio of ammonia and nitrogen, wherein 2 moles of ammonia is equal to 1 mole of nitrogen. This is to convert our moles of nitrogen into moles of ammonia. Then, to convert its unit in grams, we have to multiply it to the molar mass of ammonia, which is 17.03 grams per mole. This will give us our final answer, which is 40.9 grams of ammonia. So, moving forward, for sample problem number 2, it says that sulfur dioxide reacts with oxygen gas to form sulfur dioxide. So, if 3.4 moles of sulfur dioxide reacts with 5.0 moles of oxygen gas, how many grams of sulfur dioxide will form? For this problem, there is no given chemical equation, so we have to construct our own based on the given information. It says that sulfur dioxide reacts with oxygen gas, denoted as O2, to form sulfur dioxide. To balance the equation, we have to add the coefficients of 2 on the SO2 and SO3. Now, unlike the first problem, both of our reactants have value. So, we have to identify the limiting reactant that will dictate the amount of SO3 that will be formed in the reaction. To do that, the shortcut is to convert both the reactants to SO3, and the one that yields the lowest value will be our limiting reactant. Again, the amount of our product will be dependent on our limiting reactant. But first, we have to construct our flowchart. So we were given moles of SO2 and O2, and we both have to convert them to moles of sulfur dioxide, which is our desired compound. Finally, the mass of SO3 in grams can be obtained by multiplying it to its molar mass. To begin, 3.4 moles of sulfur dioxide must be converted to SO3 using their 2:2 mole ratio. Then, we can multiply it to the molar mass of SO3 to get its mass in grams. Similarly, we have to convert the given moles of oxygen into SO3 using their 2:1 molar ratio. Then, we can multiply it to the molar mass of SO3 to acquire its mass. Since 3.40 moles of SO2 will yield the lower SO3 value, it will be the limiting reactant, while O2 will be the excess reactant. Hence, our final answer will be 272 grams of sulfur dioxide, and we have to disregard the value yielded by the oxygen because it's an excess reactant. Now, here's another example. A solution was prepared by dissolving 1,210 milligrams of potassium hexacyanoferrate with a molar mass of 329.2 grams per mole and sufficient water to give 775 milliliters of solution. Calculate the amount of hexacyanoferrate ions in ppm or parts per million. So initially, we have 1210 milligrams of potassium hexacyanoferrate that dissociates into potassium and hexacyanoferrate ions when dissolved with water. Now, we have to find the concentration of hexacyanoferrate ions in 775 milliliter of solution and express it as ppm. To visualize the problem, let's construct our flowchart. So, we were given the mass of potassium hexacyanoferrate dissolved. We have to convert it to its moles so that we can relate it to the moles of hexacyanoferrate ions since it is our concern in our study. From that, we can acquire its mass via multiplying it to its molar mass. Then, since the problem is asking for the concentration of the ions in ppm, we have to convert the grams in milligrams and divide it to the volume of solution expressed in liters. This will give us a unit of milligrams per liter, which is equal to ppm. To illustrate, here's the 1210 milligrams of potassium hexacyanoferrate that is given in our problem. We have to convert it to grams, then multiply it to the reciprocate of its molar mass to express it in moles. Now, we can convert them to the moles of hexacyanoferrate ions, which are our main concern in this problem. Since they only have a 1:1 mole ratio, we can now multiply it to its molar mass to express the ions in grams. Then, since we have to express our answer in ppm, we can convert it to milligrams and divide it to the given volume of the solution, which is 0.775 liters. The answer will give us 1,005 milligrams per liter or 1,005 ppm of hexacyanoferrate ions. Now, for our last problem, it says here that in a gravimetric analysis, we need enough product to weigh accurately. Each tablet provides around 15 milligrams of iron. how many tablets should we analyze to provide 0.25 grams of ferric oxide product? This problem asks us the number of tablets needed to provide 0.25 grams of ferric oxide. They also gave us a relationship showing that one tablet can provide around 15 milligrams of iron. So to solve this problem, we must construct our flowchart. To trace the number of tablets that we need to have 0.25 grams of ferric oxide, we should start on the given mass of ferric oxide needed. After that, we should convert it to its moles through multiplying it to the reciprocal of its molar mass. This will enable us to convert the given to the moles of iron using their stoichiometric relationship. Then we can convert it to the mass of iron and then use the established iron-tablet relationship to determine the number of tablets that will satisfy our problem. Showing the solution, we have 0.25 grams of ferric oxide. Then we can convert it to the moles of ferric oxide by multiplying it to the reciprocal of its molar mass. Then we can convert it to the moles of iron using their stoichiometric relationship, wherein 2 moles of iron is equal to 1 mole of ferric oxide. This mole of iron can be converted to its mass through multiplication to its molar mass. Then we can express this to milligrams. What we have now is the mass of iron. And using the relationship given in the problem, where 1 tablet is equals to 15 milligrams of iron, we can get the number of tablets that we need, which is equal to 11.58 or approximately 12 tablets. So that's the end of our presentation. Thank you.